Four astronauts, one capsule, and exactly 4 minutes where absolutely anything can go wrong. Not a sensor, not a valve, not a single heat shield tile, because if it does, there is no rescue mission, there is no second chance, there is no coming back. NASA calls it the most dangerous 4 minutes in modern spaceflight, and the terrifying part? They've only done it once before, unmanned, and even that nearly didn't work. So today we're going to walk through exactly what happens during those 4 minutes, second by second, because buried inside this sequence is a problem that engineers are still arguing about, a flaw in the physics that no amount of testing can fully prepare you for. And here's what's strange. NASA knows about it, the astronauts know about it, and they're going anyway. Before we get into those 4 minutes, I need to give you the full picture, because this isn't just a story about heat and speed and atmosphere. This is a story about a bet, a calculated, terrifying, necessary bet that humanity is making on 4 human lives. Now, you've probably heard of Artemis II, NASA's first crewed mission to fly around the moon since Apollo 17 in 1972. 4 astronauts, Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen. They'll fly farther from Earth than any human has flown in over 50 years. But here's what most people don't talk about. The going isn't the hard part. It never is. The hard part, the moment where physics stops being a textbook equation and starts being a verdict on whether those 4 people live or die, happens on the way back, specifically during reentry, and not all of reentry, just one phase. A 4-minute window that the Orion capsule must survive while traveling at nearly 25,000 miles per hour, hitting an atmosphere so thick and unforgiving that the heat generated on the capsule's surface will reach 5,000 degrees Fahrenheit. To put that in perspective, that is half the temperature of the surface of the sun. Now, you might think, okay, we've done re-entry before. Apollo did it. The space shuttle did it. We know how this works. And that's exactly what makes this so unsettling. Because Artemis II isn't doing re-entry the same way, it's doing something different. Something that has never been done with a crew on board. Something that creates a physical phenomenon so extreme, so poorly understood at full scale, that engineers had to invent new words to describe what they're watching in the data, and we'll get to that. But first, let me show you what NASA is actually terrified of. Here's something that should make your stomach drop. When Apollo astronauts came back from the moon, they were traveling fast, dangerously fast. Around 25,000 miles per hour, what engineers call lunar return velocity. It's roughly 40% faster than an astronaut returning from the International Space Station. At that speed, the atmosphere isn't just a layer of air, it's a wall, a physical, violent wall of compressed gas that your capsule slams into like a bullet hitting concrete, except the concrete is on fire. The Apollo capsules handled this in one continuous arc, fast and brutal. Scorch the heat shield, deploy parachutes, splash down, done. But Artemis II is doing something Apollo never did at lunar return speeds. It's called a skip re-entry. And I want you to hold that term in your head because we're going to come back to it. And when we do, you're going to understand exactly why those 4 minutes are so dangerous. For now, just know this. The Orion capsule, instead of plunging straight through the atmosphere, is going to bounce. Like a stone skipping across water. It will dip into the upper atmosphere, slow down slightly, then rise back up into near space, then come back down again for the final descent. Why would they do that? That's a great question. And the answer involves a problem that almost nobody is talking about. Let's talk about heat. Not the kind of heat you feel on a summer afternoon, not even the kind you feel from an open furnace. I'm talking about plasma. When the Orion capsule hits the atmosphere at 25,000 miles per hour, the air in front of it cannot get out of the way fast enough. It compresses. That compression generates heat so extreme that the air itself changes state. It stops being air. It becomes a fourth state of matter, ionized gas, plasma, the same stuff that makes up the sun. And this plasma wraps around the capsule in a sheath, a glowing 5,000-degree cocoon of superheated gas, And for several minutes, the astronauts inside are separated from instant death by a heat shield that is, at its thickest point, less than 2 feet deep. Now here's where it gets strange. During the Artemis I unmanned test flight in December 2022, engineers noticed something in the re-entry data that they didn't fully expect. The heat shield worked, the capsule survived, the data looked mostly fine. But when technicians physically inspected the heat shield after recovery, they found something that made them stop and stare. The material, a specially formulated ablative compound called Avcoat, had eroded in ways the computer models hadn't predicted. Not catastrophically, not enough to endanger the mission in retrospect, but differently, in patterns that didn't match the simulations, in ways that suggested the plasma wasn't behaving the way the model said it should. And now those same engineers are trying to figure out exactly why before 4 human beings climb inside that capsule. So what exactly happened to the heat shield? NASA released findings about the Artemis I heat shield anomaly, and the details are uncomfortable. In certain sections of the shield, chunks of AV coat had broken away in a process called spallation. That's not entirely unusual. Ablative heat shields are designed to char and shed material. That's literally the point. The material burns off and in burning carries the heat away from the capsule. But what wasn't expected was the sequence and location of the spallation. The chunks were coming off before the surface had reached the temperature where models predicted it would. That means the plasma was doing something unexpected, something the equations weren't capturing. And here's where this stops being an engineering footnote and starts being genuinely frightening. Because the skip re-entry, that stone skipping on water maneuver I mentioned earlier, creates 2 separate peak heating events, 2 moments where the capsule is at maximum thermal stress. On a standard re-entry from the ISS, 1 event, get through it, you're done. On a lunar return skip re-entry, you go through peak heating, rise back up, and then come back down for round 2. And round 2, according to internal NASA documents, may actually produce aerothermal conditions that are worse than anything tested in ground facilities. Why? Because no wind tunnel on Earth is big enough. No test chamber can fully recreate the exact combination of speed, angle, atmospheric density, and gas chemistry that the real capsule will experience. The only way to truly test it is to fly it. They flew it unmanned. Now they're going to fly it with people inside. But here's what they discovered next, and this genuinely changes how you understand the entire mission. Stay with me, because up until now we've been talking about heat. But heat is the problem everyone knows about. The problem nobody is really talking about. It's communication. Or more specifically, the 4 minutes when communication is completely impossible. There is a window during re-entry, and this is real, this is physics, this is non-negotiable, where the plasma sheath surrounding the Orion capsule is so electrically charged, so dense with ionized particles, that no radio signal can pass through it. Not NASA's signals, not the astronauts' signals, nothing in, nothing out. 4 minutes of total silence. 4 minutes where mission control in Houston has no idea if those 4 people are alive or dead. And here's the part that should make you lean forward right now. During those 4 minutes, if something goes wrong, the astronauts are completely on their own. No guidance, no override, no, Houston, we have a problem. Just 4 humans, a computer, and the laws of physics. So the question isn't just, will the heat shield hold? The question is, what happens if it doesn't? And no one can know until it's too late to do anything. Let me walk you through those 4 minutes, not abstractly, second by second. Because when you understand what's actually happening at each moment, the weight of it becomes almost unbearable. T-0, entry interface. The Orion capsule hits what engineers call entry interface, an altitude of about 400,000 feet. At this point, the air is still incredibly thin, almost indistinguishable from space, but the capsule is moving at 24,500 miles per hour. The deceleration begins, and it's not gentle. The astronauts will feel up to 8 G-forces on their bodies, 8 times their own weight, sustained, for minutes, T plus 30 seconds. First plasma contact. The heat shield begins to glow, not red, not orange, white, a blinding plasma-fueled luminescence that engulfs the entire front of the capsule. The temperature spikes past 3,000 degrees, then 4,000. Inside the capsule, the astronauts feel vibration. They feel the deceleration pressing them into their seats, but they cannot hear the plasma. Sound doesn't transmit through the hull at this stage. What they can see, through the small windows, is light. Eerie, shifting, impossible light. The colors of the plasma field shifting from orange to pink to white as the chemical composition of the burning air changes around them. T+110. Blackout begins. Radio silence. The plasma sheath is now fully formed. Mission Control sends a standard comm check. Nothing comes back. In Houston, the flight director marks the time. They know this is coming. They've trained for it. But knowing something is coming doesn't make the silence easier. The silence, by the way, is one of the most psychologically brutal aspects of deep space missions that never gets discussed. Because the people in Mission Control? They're not robots. They're engineers, flight directors, and flight surgeons who have worked with these 4 astronauts for years. They know their voices, they know their biometrics, and for 4 minutes they know nothing. T+230. The skip. Here's where the skip reentry does something remarkable. The capsule, having shed some velocity in the upper atmosphere, begins to rise. It climbs back up, briefly, into near space. The plasma glow fades, the temperatures drop, and for just a moment, just a few seconds, there's a possibility of a comm window. I say possibility because this is one of the things engineers are actively working on for Artemis II. Whether that brief atmospheric exit during the skip creates a usable communications gap, or whether the ionization is still too thick. In Artemis I, they got partial telemetry data during this window. Partial, not full. Partial. Fragments of data, like catching pieces of a conversation through static. For a crewed mission, that's not enough. T+300. Second entry, the capsule comes back down. Peak heating phase 2 begins. And this is the moment that concerns engineers most. Because the capsule is now flying at a slightly different angle, at a slightly lower velocity, through atmosphere that has already been disturbed by its first pass. The aerothermal environment is different from any single entry profile. The computer models are working from interpolated data, from assumptions, and the heat shield is already partially ablated from round 1, T+345, signal returns, the plasma begins to thin, radio waves can get through again, Mission Control sends another comm check, and then they wait. 18 seconds, 20, 25. Here's the truth that takes everything we've discussed and reframes it completely. We talk about the Apollo program like it was perfection, like those missions were flawlessly engineered certainties rather than audacious gambles. We've mythologized them so thoroughly that we've forgotten the terror that was present every single time. Apollo 13, Apollo 1, the dozens of simulations that ended in failure. But even in the successful Apollo splashdowns, the ones we celebrate, the margins were sometimes terrifyingly thin. Apollo 16 Command Module, re-entry April 1972. The parachute system had an anomaly. One of the 3 main parachutes partially failed. They splashed down on 2 parachutes instead of 3. Mission successful. Crisis averted. Nobody made a movie about that. Now here's what Artemis II is doing differently, and why the comparison to Apollo isn't fully valid. The Orion capsule is significantly heavier than the Apollo command module. It's designed for longer missions, for more crew capacity, for eventual Mars-era spaceflight. That extra mass means more kinetic energy on re-entry. More energy means more heat. More heat means more stress on every single system, and the skip re-entry. NASA chose it for a very specific reason that most coverage glosses over. Without the skip, a direct lunar return re-entry would require splashing down in a much smaller landing zone, one that's harder to reach with recovery ships. The skip gives them flexibility. It lets them steer toward a safer, more accessible splashdown point in the Pacific. In other words, the skip re-entry, the most dangerous part of the mission, was chosen because it makes the rest of the mission safer. They accepted a harder physics problem to solve a logistics problem, and that's the kind of trade-off that defines the entire architecture of human spaceflight. You're never eliminating risk, you're moving it, choosing which risks you're most confident you can manage. But what haven't they fully solved yet? The heat shield anomaly. As of the latest publicly available NASA engineering assessments, the spallation patterns observed on Artemis I have been studied extensively. Engineers believe they understand the mechanism, a complex interaction between the AV coat's char layer and the turbulent boundary of the plasma flow, producing localized pressure variations that cause premature material loss. They believe they understand it, but believe is doing a lot of work in that sentence. Because the fix isn't a redesign, there isn't time for a full redesign. The fix is a refined model, an updated simulation that better captures the turbulent behavior, and a judgment call, made by engineers and managers and ultimately by NASA leadership, that the margins are acceptable. That the heat shield, even with this known anomaly, has enough margin. That 4 minutes of plasma and silence will end with 4 astronauts alive. I want to pause here. Because we've been talking about physics and engineering and heat flux and ablative compounds, but there are 4 people in this capsule. Reed Wiseman has flown to the ISS before. He's done spacewalks. He knows what it's like to look at Earth from above and feel the specific, indescribable terror and wonder of being where almost no human has ever been. Victor Glover, the first black astronaut to serve as a primary crew member on an ISS mission, a naval aviator, someone who has spent his career doing things that require absolute trust in the engineering and absolute trust in himself. Christina Koch, who holds the record for the longest single spaceflight by a woman, who has spent nearly a full year in microgravity and knows, better than almost anyone alive, what the human body goes through in space. And Jeremy Hansen, who, when Artemis II launches, will become the first Canadian to travel to deep space. These 4 people know exactly what those 4 minutes involve. They've sat in simulators. They've reviewed the Artemis I heat shield data. They've read the engineering reports. They've had the conversations with the people who built the capsule that will either protect them or fail them. And they said yes. They said yes knowing that there are questions without complete answers. They said yes knowing that the heat shield behaved in ways that surprised the engineers. They said yes knowing that for 4 minutes nobody on Earth can help them. Why? Because this is what exploration is. Not the absence of fear, not the certainty of survival, but the decision, made with full knowledge of the danger, that the destination is worth the risk. We haven't been to the moon with human beings in over 50 years, and in that time everything has changed, and somehow the fundamental equation hasn't changed at all. You want to go somewhere no one has gone. You build the best machine you can build, you accept the margins you cannot close, and you go. So, those 4 minutes, the plasma will form, the radio will go silent, mission control will watch the clock and say nothing, because there's nothing to say. And somewhere above the Pacific Ocean, 4 human beings will be pressed into their seats by 8 times their own weight, surrounded by a sheath of fire hot enough to melt steel, flying a trajectory that a computer is managing in real time based on models that are, by definition, incomplete. And if it works, if the heat shield holds, if the skip maneuver executes cleanly, if the parachutes deploy, if the splashdown coordinates are good, we will have taken the first step back, the first human step toward the moon in a generation, the first test of the architecture that is supposed to carry us back, and eventually much further than the moon. But here's the question I want to leave you with, the one that I think is worth sitting with. We've identified the heat shield anomaly, we've refined the models, we've decided the margins are acceptable. But somewhere in the gap between what we've simulated and what actually happens at 25,000 miles per hour in real plasma over the real Pacific Ocean, there may be something we still don't know, something that Artemis I data hinted at but didn't fully reveal, something that will only become clear in the moment when those 4 minutes are actually happening and there's no one and nothing that can change the outcome. And maybe, that's okay. Maybe that uncertainty is the price of doing something that matters, Or maybe it's the thing that keeps engineers awake at 3 a.m. in the weeks before launch. Probably both. Artemis II is scheduled to fly, the crew is training, the capsule is being prepared, and when that day comes, when Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen climb inside Orion and the countdown reaches 0, those 4 minutes will come for them, whether we're ready or not, whether the models are right or not, whether we've truly solved the problem or only think we have.